Hello, quick video on a project I'm working on at the moment, just a fun little educational thing. Wanted to learn more about neural networks. I made a little neural network playground sort of thing. So this came out of this cool video I watched that was linked from Hacker Newsletter by David Randall Miller. And in this video, it's really good. They create some artificial life, and each one of these dots has got a brain, and then they set various conditions on the world and iterate over many turns, many steps, and experiment with various tweaking of the brains and how they generate and all that. It was a lot of fun. It's a great video. So I thought I would have a crack at doing it myself in Go, because that's the language I'm learning at the moment. So over here we've got the world, and each one of these dots is a little creature, and if you click on them, then you can view that creature's brain on the right hand side. So we've got these circles, which are neurons, and then the lines between them, which are synapses. So a blue synapse is a positive contribution from the upper neuron to the lower one, and the red one it has a negative weighting. So if this is active, then it passes along a depressing activity onto the destination. That sounds depressing. Huh. So you can connect two output neurons from input neurons, or to or from the internal neurons. So let's find, well, there's nothing really moving, so let's give it a kick. Find one that's moving. Oh, they're all moving. Okay, so these input neurons up here are basically the sensors, and the only sense that's hooked up at the present is this heartbeat. It's just on, off every second. And so then anything that's connected to that, if it's positively weighted, gets activated. So you see this one's blinking on and off, and every time it goes red, then the output neuron goes above the threshold, which is just arbitrarily 0.75, and that creature moves up. And so that's how these things perceive the world. So they're very limited in their perceptions at the present, and how they do their stuff. So there's up, down, left, right, and random, which just moves one in a random direction if it's able. So we can fast forward things for 1,000 ticks, and there's still a bit of activity. There's a lot of things that are just banged up against the top and stuck there. So if we look at one of those, then yeah, it's up neuron. Um, it's random neuron is being strongly driven. So yeah, that's why it's doing what it's doing. Um, so I've also got this button here for cull population, which kills everything that's not in the left hand, like 3 columns or so. So this is the selective pressure that David, yes, used. That basically, in order to have some selective pressure on the system, we have to give some reason for it to evolve. Otherwise, everything's just sort of bobbing around happily. Um, so so now we've only got 3 survivors, and this is what their brains look like. And now we can top up the population by using this connectome to generate another 97 crits. So let's do that. So there we go. We've reset back to the starting state, and you notice that there's a fair few moving to the left, because those ones have inherited the knowledge, or inherited the connections that say, hey, when the heartbeat sense goes, I should move left. So here's this strong positive relationship here. So if we step this world forward by 1,000 ticks, there's a fair few things grouped up on the left there. So let's cull again, top up the population. And now there's a lot more moving over to the left. So let's do that a few more times. Cull, top up, 1,000 ticks, cull, top up. And so now you see, now the moving to the left behavior is more or less universal. So when we do this cull and then top up, it's taking all of the brains of all these creatures, and the survivors just get randomly distributed back into the world again. But for all the new ones that are created, they get a brain copied from one of these ones and then mutated a little bit. So we flip 10 random bits in each brain, and that makes their connectome slightly different, and the biases on each of the neurons. Because these are sigmoid neurons, so they've got the various numbers that control how they behave. They've got a bias that this is this number down the bottom here. So you see that this survivor has quite a high bias on its random movement and on its left movement, which makes sense. So the random movement is helpful for this situation where you get stuck up against someone who's not moving left, but you're trying to move left. See, this pink one here is trying to move to the left, but it can't. It's blocked by this one. So if it's random with firing, then it could boop up or down or whatever and get past it and get over to the safe zone over here. Because there's only like enough space on the left hand here to have, if everyone is thinking properly and making the smartest decision, then they can fit inside the boundary over here. But because there's these occasional blockers, they can't get there. So I've done this process a few times, like 1,000 ticks, cull population, top up population. But I can also just click this button, which will just do 10 cycles of that. And so over time, we'll end up with a pretty homogeneous set of behaviors. In David's video, he colored the dots based on the genetic diversity. I tried to do that. I've not done a good job. I think I might need to calculate the hue based on the connectome, because at the moment I'm assigning red, green, blue based on just 1/3 chunks of the connectome. So yeah, you can see right now that the moving left behavior is pretty much universal amongst all things. So the code is actually pretty straightforward. So it's all up on GitHub. I'll put the link in the description. So there's basically the static website, which is just the click handlers for the buttons, and then the world and the brain. Very, very basic, and then some script to update the images, and then make a request to the server if you click on the world picture. So if you've not used Go before, it's a remarkably readable language. But breaks down basically, there's the main function this is the entry point that sets up all the handlers for the web server, and then sets up the world, and then starts it ticking once a second. And so the world just sets the rules of the world and does the checking to see whether it's valid for something to move somewhere. And when it initializes, it creates a certain number of random critters. The critters handle the sensors and the brain, and then the brain has all the neurons and the synapses, and so they all work together to produce this behavior. There's a few other selective pressure ideas that David went through. He had one where every 10 seconds or something, it would kill everything on the left, and then it would kill everything on the right to train the creatures to move back and forth across the space. I also want to add some more sensors to detect adjacent creatures. And then maybe start looking at stuff like predator-prey things, like if you are hungry, and like one of these neurons might be hunger, and then one of them might be prey adjacency or what have you. But I don't know. We'll see how we go. But it's been a fun little project. And this video I'll link in the description. It's really worth it. It's great fun. My neural network experimentation is quite basic. It's not very efficient at all. There is this really awesome write-up on base principles neural networks. They go through a lot of examples on this bloke, Michael Nielsen. Really, really good article. Starts from the bare bones and works its way up from there. I haven't incorporated a bunch of the learnings in here. This is more focused on machine learning in general and gradient descent and much cleverer stuff than what I'm doing. But it taught me about sigmoid neurons and how cool they are. Their activation functions make things a lot more sort of organic. Okay. Wow, that's almost 10 minutes. That was longer than I thought. Okay. Bye-bye.